Hi, everyone. My name is Jackie Baek. I'm a PhD student at MIT, and I'm very excited to share with you this work called Fair Exploration via Axiomatic Bargaining. And this is joint work with my advisor, Baek. So we all know that algorithmic systems are becoming more and more prevalent in all aspects of our lives, and these systems can have a profound impact on society. So this means that if the algorithm displays some sort of undesirable disparity, this disparity will also have a large societal impact. So for example, precision medicine is an emerging application where the use of algorithms can have a huge impact. But there is some concern that precision medicine is actually going to deepen the inequities that exist in the current healthcare system. And so the whole field of algorithmic fairness identifies and addresses these issues. And so a typical setup in the algorithmic fairness literature is to use the offline machine learning setting. So essentially we tweak the algorithm so that its output or its decisions are more fair for some definition of fairness. So this is one approach, but this approach is inherently constrained because oftentimes the source of the disparity is actually caused by the data. And for example, in the precision medicine setting, the concern is that we have data on what treatments work well for a particular group of patients, but this data set is not representative of the entire population that we're interested in. And if the issue is caused by the data, then we can only do so much by tweaking the algorithm. This is not going to solve the root issue. So the sort of obvious solution to this sort of problem is to collect more data. And a natural framework that captures the data generating process is to use the online learning framework. So using this online learning framework, the algorithm essentially has some control over the data generating process. So if the algorithm deems that the current data set is insufficient to properly learn, then the algorithm can go out and collect more data so that the policy can be improved in future time steps. And this process of going out and collecting more data to improve the algorithm is what's called exploration. And this is a well-studied process in the field of online learning. So there are many exploration-based policies for online learning that provably eventually learn the optimal policy. And what I mean by optimal policy is the policy that, for example, in the precision medicine setting, would give every patient the best treatment for them. And so this is in some sense the best possible policy one could hope for. Sort of for everyone, we know exactly what their best treatment is. And online learning will get us there. But of course, good things don't come for free. What is the main downside of using online learning? The downside is that exploration can be costly in the short term. And this is the essence of the exploration-exploitation trade-off. So for example, in the precision medicine setting, if you want to learn about a particular drug, we have to try the drug on some set of patients. And if the drug ended up not being good, then these patients kind of incurred this cost of exploration. So given that online learning has these upsides, but also comes with these downsides, the problem that we study is sort of what are the possible societal implications of these downsides? In particular, can these downsides result in some sort of unfair outcome? And so the answer to this question is yes. And the type of unfairness that arises from exploration is something that has not been well studied in the past and has been barely identified as a problem prior to our work. So one of the high-level takeaways from our work is simply the fact that naive exploration strategies can lead to undesirable disparities. And therefore, as algorithm designers, we have to be careful when designing algorithms for exploration. So let me give a roadmap of what this talk will entail. So we study the most fundamental online learning model, which is the multi-arm bandit problem. And so in this setup, the question that we ask is, what is a fair division of exploration across multiple groups? So given that exploration is necessary, but it comes with a cost, how should we allocate this cost across multiple groups of people? And so to answer this question, the first thing that we need to do is formalize a notion of fairness. And we formalize an axiomatic notion of fairness using the well-studied cooperative bargaining framework from economics. And so once we have a framework to talk about fairness, we can start evaluating policies on whether they are fair or not fair. And we show that efficient policies are unfair. And we develop a new policy that we prove is optimally fair. And we show that it only comes with a small compromise in efficiency. Okay, so this is the outline of the talk, and now I'm going to describe the main problem, the model, and the framework, the fairness framework, and I'm going to describe this by walking through a case study that we did on warfarin dosing. So, okay, so warfarin is a drug. It is a commonly used blood thinner, and it has the property that the optimal dosage of warfarin varies highly across patients. So essentially, we want to learn, we're going to tackle the problem of learning the optimal personalized dosage of warfarin using an online learning setup. So essentially, at each time step, one patient arrives, we observe their covariates, and we have to take an action, which is assigning them a particular dosage of warfarin. And if patient X gets an action A, then we assume that the reward is a linear function of the covariates and theta of A, which is an unknown parameter. So there's a different theta for each action. And so for every patient, basically the optimal action is to give them the action with the highest reward. So this is sort of the optimal policy. And this is sort of the canonical linear contextual bandit problem. So there are standard bandit policies for this problem that will eventually learn the optimal policy, that will eventually learn for every X what is the optimal action. But to eventually get there, to learn the optimal policy, we're going to incur some regret. And here you can essentially think of regret as the number of mistakes made by the policy. So every time we assign an action that's not the optimal action for that particular patient, our regret increases. And clearly we want this regret to be as small as possible. And this is the standard notion of the metric that's studied in the bandit literature. But what we're interested in is actually not exactly regret, is we're interested in group regret, which is the regret incurred by each group. And here we're going to use the race of the patients as the group. And so basically what we're interested in is how the total regret is divided among patients of different groups. So does the policy make more mistakes on certain groups of patients and less mistakes on another group of patients? So we have a publicly available data set on warfarin dosing. And so we derive a contextual bandit instance where we use the race of the patients as the group, and we evaluate a regret optimal policy, but we're interested in how the regret is distributed between these two groups. So here are the results. There's two groups called A and B. And so this is the group regret, and these numbers are appropriately normalized. So it sort of accounts for the prevalence of the groups. And so basically we're interested in whether this is a fair outcome or not. And in particular, the question that we ask is each group taking on their fair share of exploration? So even though one group group B incurs much more regret than group A, I claim the answer to this question is not clear from looking at these numbers. Because what if it's the case that patients of group B are innately harder to learn than patients of group A? So when would this happen? Maybe patients of group A are completely homogeneous. They all have the same covariates, whereas maybe patients of group B, they're more diverse, and therefore the policy needs to do more exploration and make more mistakes in order to learn the optimal policy for patients of group B. In that case, it would make sense that group B has a much higher regret than group A. So essentially, to understand this issue, we actually can't just look at these two numbers. What we really want to understand is the extent of cross-learning that's happening between the groups. So right now, exploration or learning is something that's shared between the groups. So if one group explores and learns something, it could potentially benefit the other group and vice versa. And we want to understand the extent of how much this is happening. And so to do this, we're going to consider the hypothetical scenario where each group is on their own and therefore would need to do the exploration on their own. So for example, if group B didn't exist, then we would expect that basically group A can't rely on group B to do some of the exploration for them, and they would have to explore by themselves. So we would expect that group A would incur more regret than the 5.9 that it incurs when each group is when the groups are together. So we evaluate this hypothetical scenario, and here are the results. So the main thing that we see is that when each group is on their own, the regret incurred by each of the two groups is actually very similar, 74 versus 78. So it means that it's actually not the case that group B is innately harder to learn than group A, because when the groups are separate, they incur a similar amount of regret. But when the groups are together, Group A's regrets reduces substantially, which means that Group A is benefiting a lot from the presence of Group B. And so we're going to call the difference between these two numbers the utility gain. And this represents for each group how much they benefited from the presence of the other group. So we're going to now view everything in terms of this metric, utility gain, and we're going to define fairness with respect to this number. So to formally define fairness, I'm going to show you a series of pictures. So we're just sort of plotting the utility gain. So the point that we have is here, this purple point. And so essentially the blue point, the origin, represents the outcome when each group is exploring on its own. And the utility gain, we're measuring how much does each group benefit relative to this point. So we're redefining this outcome as the reference point or the origin. And so the question is whether this purple outcome is a fair outcome or not. And so whether this is a fair outcome or not depends on what other outcomes are feasible. So if we run a different bandit policy, we would get another point on this plot. Maybe we would get this red point here. And so, if these 2 points, the red point and the purple point, are the only 2 possible outcomes, then clearly that we would prefer the purple point because both groups have higher utility gains under the purple point. But of course, there are many, infinitely many bandit policies that one can run. And so what we're really interested in is we first want to understand what is the whole space of feasible outcomes that are possible under some bandit policy. So for now, we're just going to assume that we know what this feasible set looks like. And let's just say it looks like this. And so given we know what the set of feasible utilities look like, what is the most fair outcome in this feasible region? So to answer this question, we're going to go back to foundational economics and use what's called the axiomatic bargaining framework. And so how this works is that there are a set of axioms that are deemed desirable for a fair solution. And these are sort of well-established axioms from the welfare economics literature. So I won't go through these axioms in detail, but essentially the seminal work of Nash in the 50s showed that if you want to satisfy these axioms, then there's actually a unique solution. It's just called the Nash solution. And this solution is easy to actually state. It is the point that maximizes the sum of the logs of the utility gains, or equivalently maximizes the product of the utility gains over the groups. So essentially, if we have this feasible region, we want to find this point that maximizes this objective function. And this notion of fairness is also called proportional fairness. And so this is how we're going to define fairness in our model. And so more specifically, what we want is we define the fair policy to be the bandit policy whose induced utilities map to this, this green point. Because right now, this plot is in the space of utilities, but what we really want to optimize over is in the space of bandit policies. So we want to find the bandit policy that achieves this Nash solution, and this is what we do in our paper. So let me actually show you what happens when we plug in this, the fair policy that we find back into this warfarin example. So what we had before was this purple point, and this is actually, this outcome was from a regret optimal policy. So this purple point is actually the efficient solution. But the fair solution we get is here. And we see that essentially the utilities are balanced out between the two groups. And but in terms of sort of relative changes, the utility for group B increased by more than 300%, while the utility for group A decreased by only 28%. And if you look at the total utilities, the fair solution actually has a total utility that's actually very similar to the purple solution, and the purple solution is the one that has the best total utility gain. So essentially in this example, the price of fairness is small. We're able to get a fair solution without compromising too much in terms of total efficiency. Okay, so this is the result on this particular instance. So now I'm going to spend the rest of the talk going over these sort of natural questions that arise from this setup. So let me just quickly describe the questions. The first one is, how fair are regret optimal policies? So since the whole the entire bandit literature essentially tries to develop policies that minimize total regret, this first question is asking, okay, if we use one of these regret optimal policies, how well does it do in terms of fairness? And the second question is, can we find a policy that achieves the Nash solution? And the third question is, how efficient is the Nash solution? So now let me just get started on answering the first question. So, so to answer this question, I'm going to describe a model called the group K-arm bandit model. And this is the simplest bandit model that captures the phenomenon that we're studying. So we start with some set of arms. We start off with a K-arm bandit model. So each arm has some reward of theta K. And we have the notion, and we have groups. And each group is going to be associated with some subset of arms. And basically at each time step, one group is going to arrive, and they only have access to the subset of arms that it's associated with. So we have to assign them one of the arms that they have available. And we're going to define theta star as the best reward for that particular group. And we define the most disadvantaged group as the group with the smallest theta star. So the most disadvantaged group is the group whose best option is the worst. So under this very simple model, the result that we get is that under any regret optimal policy, the utility gain for the most disadvantaged group is 0. So if you run any policy that minimizes total regret, there's going to be one group, namely the most disadvantaged group, that is actually going to incur the entire burden of exploration. And the intuition for this result is that the most disadvantaged group actually incurs the least regret from exploring. So a regret optimal policy will use this group to explore, right? So for example, in this simple instance with 3 arms and 2 groups, if this is the true relationship of the arm means, then the regret incurred by group A from pulling arm 2 is smaller than the regret incurred by group B from pulling arm 2. So actually group A, it's more efficient for group A to explore and incur the regret than group B. So we get the sort of the most unfair outcome when we run a regret optimal policy. So then the next question is, okay, can we find a fair policy? And so the first thing we need to do is we need to first characterize the space of feasible outcomes. So I won't go into the details of how we characterize the set, but we are able to explicitly write down this set, big U. And essentially we want to maximize the sum of the logs over this set. But the main problem we run into is that the space big U is a function of the parameter theta, which is the underlying bandit parameter that we don't know. And so the main idea is that we're going to solve the optimization problem with using an empirical estimate of theta hat. So, so this is what the policy looks like. I won't go through it in detail, but essentially the main idea is that at each time step, we solve the optimization problem of finding the Nash solution using an estimate of theta hat, and we sort of try to follow this solution. And we prove that this policy achieves the Nash solution for all bandit instances. Okay, so lastly, the question is, how efficient is this Nash solution? And to understand this, we analyze the price of fairness, which is capture sort of how much utility we're losing in comparison to the efficient solution. And so we show a theoretical result. This is a worst case upper bound, which is a function of the number of groups G. So this upper bound is small when the number of groups G is small. So this is a worst case bound, but we also show sort of on an average case when we randomly generate instances that the price of fairness is actually very small, actually much smaller than this than the upper bound, the worst case upper bound stated in the theoretical result. Okay, so these are the main questions that our paper studies, and sort of to give you a 2-sentence summary of these results, we show that the efficient solution is unfair, but the fair solution is almost efficient. And okay, and that's it. Thank you so much for listening to this presentation.